took a family of topological spaces. Right, I'm just recalling what I did there. I take a family of topological spaces are taken, and how we created this product space. Of course, this is always there. This is just a set. The kind of topology we created on this is from the subbase topology. We have a subbase is a collection. Yes, consists of all. You know, um, there are other ways. Okay, set of all pi g alpha in delta, where each g alpha is open in alpha, is open in x alpha, and only except from one alpha, everything is x alpha. G alpha is x alpha for all but one alpha in delta. Okay, so I have taken one component is some g beta, rest of them are x alphas. Everywhere else is x, etc. So these are the kind of things we said this forms a subbase for some topology. Okay, why does it form subbase for some topology? Any collection of sets forms a subbase for a topology provided its union is the whole space. That's all. Its union is the whole space. Of course, it is the case. In this case, pi x alpha in delta itself belong to S, and therefore union of all the members of that is X. I can call this X. Okay. So if there is an S, then S will definitely be a subbase for some topology. Therefore, S is a subbase for some topology on X. Okay. Of course, what is the base for that? The base B is finite intersections of these things. So you can easily see that if I take G alpha, everything is XX with some suffixes, some alpha dash and so on, so XXX, etc. Suppose you have intersected that with okay, why you can easily see the following: pi G alpha alpha in delta 1 pi G alpha in delta gr second. This is one subbasic set. This is another subbasic set, and so on. I have a whole lot of subbasic sets. Maybe G n alpha in delta. These are the subbasic sets, and their intersections is what makes up the basis, right? B is what intersection Sk k equal to 1 to n, where S1, S2, etc. Sn is a finite subcollection of S are members of S. Okay, S1, S2, etc. Sn are members of S. So when you take S1, S2, etc. Sn and you intersect them, it is very easy for you to see that this intersection is alpha in delta G alpha 1 intersection G alpha 2 intersection, etc. intersection G alpha n. Okay, that's easy to see that, because if you want a x alpha in delta to be in it, if you want it to be in this intersection, it should be in this. That means the alpha coordinate is in G alpha 1, in G alpha 2, etc. G alpha n. That means alpha coordinate is in this. Therefore, the whole thing is in this. So I think it's not a big thing. So you might as well see, therefore, this is nothing but such things. What is this? Product G alpha in delta, where finitely many of them okay, is what you have infinitely many. This is actually is very easy to see that infinitely many places. This is nothing but finitely many places are G alphas in X. So this is like each G alpha is open. Okay, for each alpha, G alpha is open in X alpha, and G alpha is X alpha uh, for all but finitely many alpha. For all but finitely many alpha. That is what our definition is. Okay. So that is the actually the thing is very tempting. Why are you taking only open sets only in finitely many places? Why did you take open sets all over the place? Yes, you can do that also. Even that also forms a basis. I want to just say one or two words about that in a few minutes. So this is what we have done, and this has created a topology. Topology B is a base for some topology. On X equal to product X alpha, alpha in delta, okay? And that is called the product space, okay? X with that topology is called the product space. X with that topology is called the product space, okay? You have another topology we introduced later on, what's called box topology. That's a different topology. And which you will notice in later through some examples that is more of the kind of topology that we would prefer, not the box topology. We'll come to that. Okay? So what we did more is for each alpha, for each beta in the index set delta, I have the phi beta, which is the projection. I should write small pi. That's my. Some people write p also. Phi beta is a mapping from product X alpha, alpha in delta to the beta component. That's a projection. So the entire, maybe it would have been easy if I just took the two topological spaces, n topological spaces, and so on. Okay. I think you understand what I'm doing anyway. So I'm projecting a, a delta tuple onto one of its components. That's why this is called a projection map. Is the projection map. I think in Siemens you just p beta there. I'm so used to using pi beta, so I use that. Okay. Siemens uses a projection map to be p beta. Is the projection map onto the beta coordinate space. And I think it's very easy for us. I have told you that this p beta, pi beta will be continuous. So if you pull back an open set, what do you get? Everywhere else is full space, and in that open set, you get open set. So as a matter of fact, pi beta inverse an open set G in X beta. Okay. For any open set G in X beta, what is pi beta inverse G? It is actually going to be product G alpha, alpha in delta, where G alpha equal to X alpha for each alpha not equal to beta, and G beta equal to G. Does that make sense? Is that clear? When you pull back the G beta component, all the other things are free. They can be anything. It's only the beta component going there. What are the other things? Everything, in this component, I have x beta. Everywhere else, whatever it is, where will this project go? Only to x beta. So what I can keep is anything I can keep here. So when you invert this x beta comes, they're all also, there can be anything. So that's why pi inverse G is actually nothing but in the beta component put G, everywhere else you put the full spaces. And that is a basic open set. This is a basic open set. So therefore, right? So pi beta inverse G is open. Okay? Is in yes, and so is open. And so is open. So therefore, each therefore each projection phi beta is continuous. You know what? Each pi beta is open also. If you really look at the what happens, only the component goes there. Pi beta is even an open mapping because it sends open sets to open set. Any open set in the product space looks like that. When it is projected upon to beta, the beta component alone comes. Okay. Also, pi beta of pi g alpha in delta is g beta. So the projection map is open also. So pi beta is open too, is an open mapping. So pi beta is both continuous and open. Okay, right? Actually, I want to. Yes, go ahead.
So we defined pi beta in such a way that this projection mapping, the beta component will map to beta. Everything else is basically left alone, right? If we defined it that way, then pi beta inverse. Yeah, we'll come back to that beta. Okay, this all makes sense. That's the definition of pi beta essentially. In a way, yeah, yeah.
When you pull back, everything is there.
Yeah, yeah.
Only the beta component ought to be G.
Yeah, it doesn't have to be 1, but yeah.
Yeah, beta component of G. Rest of them are all there. Everything goes to that beta. So
beta.
when you pull back, you can keep everything. That's why a pi beta inverse is only the beta component is G. Everything else.
Yeah.
Actually, pushing forward. Okay. So it's both an open mapping and a continuous function, except it's not a budget mapping, right? So it's not like home you mapping by anything. Okay. It's open mapping we defined in general any function from topological space X to topological space Y is called open mapping. If open sets are pushed forward to open sets. So if I will open set G in X, f of G is open in Y, then that is an open mapping. So the each phi beta is an open. Okay. You know, I would actually want you to think a little carefully. This is also true. Indeed, the product topology, the product space topology on pi x alpha in delta is the weak topology generated by the family of all functions pi alpha, maybe I should say, yeah, pi alpha in delta. Can you visualize that? So what is that? Pi x alpha in delta, each pi beta is going to x beta. If I want each pi beta to be continuous, I want every pi beta inverse open set here should be an open set in the product space. And this is a sub-basic open set, really. So all the sub-basic open sets are actually inverse images of pi betas of open sets there. All right. So our discussion starts from here. I want to say that actually the product space and uh, pi x alpha alpha in delta is the weak topology generated by these things. Because what are all these things? If every projection map has to be continuous, the inverse image of open sets and every projection map should be an open set here. But what is pi b inverse g? It is nothing but a pi g alpha alpha in delta, where every g alpha is x alpha if alpha is not beta, and g beta itself is g. So it's a subbasic open set. Okay, so when each of these is continuous, all the elements I have, which are supposed to be in the subbasic open sets, are actually sub open. I require. Okay. So in order that each pi beta is continuous, I want to make sure these are all the open sets. Of course, these are the open sets I used to generate a base and hence a topology. So I think there is a minimal structure I need to give you the product topology. What is that minimal structure? The inverse image of p beta pi beta with respect to open sets in X beta. And therefore, that statement is clear. Can I say that or not? You can come back to me. Tell me. Weak topology means the smallest topology I can have on the space with respect to which all these projection maps are continuous. For projection maps, if you want projection maps to be continuous, all sorts of sets should be there in the topological space, but they form a sub-base, and therefore they give you a topology, and that is the topology which I am calling product topology. So bare minimum I want is the open sets of the product topology should be there in the topology for all this to be continuous, and they should be there. So weakest topology is that. Product space is the topology. Okay,
Yeah,
sir?
we created a sub base. From there, we created the base. From there, we created the topology. We are just basically reversing back and we're saying that this is the sub base you get. Yeah.
And we're not requiring any more than that.
Yeah.
For these pi beta to be continuous, we only want them. Okay. So that is the weakest topology amongst all topologies with respect to which all pi betas are continuous. So this is so the topology generated in the product space is nothing but the topology that makes all these projection maps continuous. I think everybody understood that. Okay, good. And here is a little theorem, not a really big thing. It's easy to understand. Let Y be a topological space. So I already have pi x alpha with product space anyway. And f is a function from y to pi x alpha alpha in delta. Okay. So I have this pi x alpha alpha in delta, and I have this mapping f from y to that, and I have this projection map to any projection beta, which is pi beta, and their composition is pi beta circle f. Okay, I will show to you that f is continuous if and only if pi beta circle f is continuous for every beta. Okay, then f is continuous if and only if pi beta circle f is continuous for every beta in delta. Okay. Yeah, I think that is also very clear. If f has to be continuous, inverse image of open sets must be open sets here. But Actually, inverse image of subbasic open sets or open set is good. But every subbasic open set comes from the inverse image of an open set in X beta. So I think I don't have to prove this theorem after all. If you take any open set, inverse image is subbasic open set, that inverse image is in this. If F is continuous, then the pi beta circle F is continuous. And the other side, if pi beta circle F is continuous, so you have to show that if every pi beta circle F is continuous, you have to show that F is continuous. I think it's nothing there. I see that. Maybe we'll write a proof. Why not? So yeah. Anyway, if you take an open set, yeah, and that open set pulls back to an open set here. If F were continuous, it pulls back to an open set here.
Yeah,
And so therefore,
same argument. Yeah, similar argument. Basically, it needs to pull back into an open set from x beta to pi x alpha, from there to y. So that means x beta to y will be open.
so nice.
Right.
Actually, it's just a matter of notation. If the notation sinks in, these are obvious. Okay, and the diagram shows what's going on.
Then why do we have to do? Why it has to happen for every beta?
Yeah, because see, if for continuous, every subbasic open set should be pulled back to open set here. But for every beta, the inverse images are the subbasic open set. All subbasic open sets will pull back. Whatever pi beta doesn't matter. When you invert, you get another subbasic open set. In the beta of the component, that open set sits everything else x alpha. And that can be pulled back to get an open set here. That is why I can put every pi beta. On the other hand, if I want this to be open, if you want pi beta circle F to be open, yeah, for every beta, F is open, you have to prove. That is also the same story. If I take a pi beta circle F inverse, if I take an open set in that G, in that, it is actually F inverse circle pi beta in F inverse of pi beta inverse of G. Yeah, that actually clinches everything. If every such set is open for every beta, okay, then F inverse of every subbasic open set is open. Therefore, F is continuous. I proved the converse also. Okay, so this follows from here. Let me explain that. Maybe I'm a little too quick in saying that for every beta in delta and open set G in X beta, okay, pi beta circle F inverse G is F inverse pi beta inverse G. That finishes the problem. Okay, I will read this step by step. First, if F is assumed to be continuous, pi beta is anyway continuous, and therefore their composition is continuous. So pi beta circle F is continuous for all beta. Conversely, if I assume every pi beta F is continuous, so for every pi beta F is continuous means no matter what beta I take, no matter what open set I take, pi beta circle F inverse G is an open set, which means F inverse such open sets are open. But such open sets are the, as beta keeps going back and forth and G becomes an open set in such open sets are all the subbasic open sets. So this is amounting saying that F inverse of every subbasic open set is an open set, which means F has to be. So, this way.
Okay.
This proves the result. Result follows. Okay. Good. I mean, I'm saying that things are very easy if you understand the notation. Actually, yeah, then we'll ask, well, what is this box topology you're talking about? It's very interesting. Why not? Why are you taking only, only open sets in some components and everywhere else only X alpha? You are actually the basic open sets in product topology is like only finitely many components are genuine open sets in the corresponding topological spaces. Rest of them all are full spaces. So I'm tempted. Why don't I introduce another, maybe is something like that, pi g alpha alpha in delta, where each g alpha is open in X alpha for each alpha. I'm not asking that all but finitely many must be full spaces. Yeah, you can prove that that is also a base for some topology. Okay, here is box topology on product space. Okay, so skip B is set of all product G alpha alpha in delta, where G alpha is open in X alpha for each alpha in delta. So it's okay if a very open set is taken. Will that be a base for some topology? Of course, we have to check that. What is the condition for something to be base for topology? Union of all the members of the basic elements that you contained is the whole space. And if you take two basic open sets, if you take two sets B1 and B2 in B, their intersection, in the intersection, if you take a point X, I should be able to squeeze in a B3 between X and B1 intersection B2. Okay. If that happens, that will be a base for some topology. We can verify that. First of all, product X alpha, alpha in delta is already in B because each is an open set there. And therefore, union of all basic sets B in B will be X because X itself is there already. Okay. And if B1 comma B2 belong to B, okay. Well, say B1 is actually maybe product G1 alpha alpha in delta, and the B2 is product G2 alpha alpha in delta, right? Where G alpha 1 and G alpha 2 are open sets in X alpha, and finally many of them are only genuine open sets, rest of them are all full spaces. If I take them, okay, then it is easy for you to see that B1 intersection B2 to start with, which is really pi alpha in delta G alpha 1 intersection pi G alpha 2 intersection. But you know very well this is nothing pi G alpha 1 intersection G alpha 2 alpha in delta. Oh, that means that is itself because G alpha 1 and G alpha 2 are open sets in G alpha, their intersection is also open set in G alpha. Both of them are full spaces, the intersection is all. This B1 intersection B2 itself is in B. There's no need to ask or to squeeze one. If you take an X, that B3 is going to be B1 intersection B2 itself. So yes, these two conditions says therefore B is a base for some topology on X. So I called this space the box topology. And this is called the box topology. The box topology on this product. Actually, we'll not use box topology much. Box topology does give you interesting counter examples for several things, but one will ask, this is also a very nice topology. Why are you biased towards the product topology, not the box topology? One would ask. Let us see. Let us see. There are some things that we naturally expect from the product space. Box product topology actually lacks. It lacks in some of the basic things you are hoping for in product space, as you will see. Okay. Actually, here also, one thing is that I have more open sets in the box topology, isn't that right? So
That's
right
right.
away, box topology is stronger than the product topology. So note. Box topology on x equal to pi x alpha, alpha and delta is stronger than the product topology on x. Okay. Actually, this is too strong a topology. That, that's what I'm. It's too strong a topology for us to actually uh, use it well, as I'm going to show you through some examples. Okay.
Is there a notion of a max topology? It's essentially every possible element is in there, essentially. Right? If you take any topology on X, that is actually weaker than this box topology.
Oh, no, 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 no. You can take the upward topologies, which have nothing to do with the product structure at all, also, right? You may define some topological space on that.
That
Who's
may
open?
not actually, okay.
Yeah, so that's also an issue. Okay. Yeah, if I'm only looking at product space, and so, okay, yeah, you understand that, right? Hmm? But I said that it's very strong and it is so rigid and you will have little troubles. I will show you through one example to demonstrate what it is. Okay, one thing is in case, uh, uh, in case delta is finite, then both topologies are the same. Is that right? Then both topologies are same. Both box topology, box topology, and product topology are the same,
Mm.
are both the same. Okay, is that right?
No, I
Now,
didn't. I
oh,
don't
if I'm only
say it.
finitely many, suppose x1 into x2 into etc. into xn, suppose that's all I have. Okay, yeah. A product space in box topology will have the same open sets. Because what are the open sets in the product space? Basic open sets are like keep open sets in finitely many components. That means in all components you can keep open sets and create those sets. They are the open sets in the product topology.
Okay. Yeah. Right. Right.
Okay, so if the number of indices that I have delta is finite, okay, if the delta is finite, then both are same. Only when you have infinitely many components, you have trouble. Okay. For example, let's look at R omega. R omega means R uh, uh, for each natural number I have one R and uh, I have crossed that this. So this is like that means what is R omega? For each natural number n, xn is R and R omega is product xn n equal to 1 to infinity. That is R omega. Omega is the set of all natural numbers. Okay. Um, So this is like sequences, right? And if I look at the function f from R to R omega, defined by f of t, f of x equal to f of x equal to x forever x, all are x. Okay, you can see that every projection pi alpha circle x at x is x. Okay, so this is an identity mapping. This is a mapping from R to R alpha is R. This is the alpha component. Okay, identity function is continuous. So every pi alpha is continuous for every alpha. Therefore, f is continuous with product topology. Okay, R omega endowed with product topology. Right? So every projection map is continuous. I mean, a pi alpha circle left is continuous for every alpha, therefore f is continuous. It's a continuous map. Okay. Now let me put box topology on this product and see what happens, whether this function is continuous. You will notice that this function is not continuous if I put box topology on R omega. Okay. If now suppose R omega is endowed with box topology. Suppose I have box topology here. Now, so if I want this function f to be continuous, every open set here should be inverted back to an open set in R, right? So I take an open set on the right hand side. Let's look at the open set -1, 1 cross, minus half, half cross, minus 1/3, 1/3 cross. You have countably many. Yeah. Let's look at this set G. Is open in R omega because I can have all components are open sets. Infinite many components are open sets. Okay, is open in R omega, and that's function same function f. Okay, and what is f inverse G? Is that going to be open? F inverse G, I claim cannot be open in R. Actually, these are all around 0, 0, 0, 0, right? 0, 0, 0 there.
Yeah.
F inverse G, I claim, so is open in omega, and it is a neighborhood of
F0.
0 bar. If you allow me to say 0 bar, 0, 0, 0, 0, etc. Okay. So I have inverted this. 0 is an element in this. I want to claim that F inverse G cannot be open. We claim F inverse G's are not open. If it is open, that 0 will be interior point. If F inverse G were open, then 0 is an interior point. So there exists a delta greater than 0 such that minus delta to delta are to be contained in F inverse G. Therefore, f of minus delta to delta should be in G. Okay, right? Therefore, f of minus delta to delta has to be in G. What is f of that? Each component is xxx. So it has an nth component. As a matter of fact, nth component of f of this, nth component of f of minus delta delta, that has to be in the corresponding component of G. That means this has to be contained in minus 1 by n, comma 1 by n for all n. But this is just minus delta delta only. F is only leaving x to x. Every element x is going to x, right? So that's why, if the component is whatever is given, that is what is coming out. Giving minus delta delta, the minus delta delta. Oh, I can't have this for all n. It is not possible. Because it's totally becoming small, and how can that be contained inside? That is not. This is impossible. This is not possible. So that f, which is continuous with respect to the product topology there, which is a very nice function, is not continuous with respect to the box topology. Okay, therefore, f is not continuous with respect to box topology on R omega. Is that clear? I can give you something more. I'll just briefly say, maybe I'll write this one here. I can briefly say the following. You can actually talk about convergence of sequences in a topological space. In a topological space, if I've taken a sequence of elements, anyway, before I go, are you okay with this discussion?
Yeah, this makes sense. Good.
So indeed, I don't even have that. I don't even, it's a, what is that? All the pi n's are continuous anyway, because this is a stronger topology. All the projections are continuous, right? Because I have a big topology. But the pi n circle F is not continuous for all n. Okay. Anyway, F is not continuous. I'm not insisting that pi n circle F should be continuous for all n. I'm not saying anything of that sort. Because all pi n's are continuous. If F were continuous, yeah, pi n circle F should be continuous too. But yeah, this is what it is. Okay. Maybe as a sample, I would like to say something more to recognize that box topology is not will not be so nice as you really wish it to be. Okay, though it is a wonderful topology, it gives you a lot of examples. It's not as nice as you wish it to be. For example, you're talking about convergence in a topological space. We can talk about it. Then, if you have infinitely many copies of R, in that also you have sequences. And what is the convergence of the sequences in that would look like? I would naturally expect, I think, component-wise convergence is reasonable for convergence in the topology. But you will notice that in the box topology, such a convergence becomes very, very too stringent. Okay, let's see. Let's take an example and move forward. Okay. So here's the definition of convergence in a topological space. Let X be a topological space. Okay, we say a sequence Xn in X converges to X in X as n tends to infinity. If for every neighborhood of X, okay, and Professor says all these X's should fall in. There exists a not a positive integer such that Xn is in G for all n greater to n. Is that a meaningful definition? For every neighborhood around X, another of the says the Xn's have to get into that G. That's when we say that Xn converges to X. Okay. You see, this is a very abstract definition, because if you look at the indiscrete topology, okay, now I think every sequence converges to every number. Is that clear?
Right.
Every sequence converges to every number. The limits are unique and all those things were not there. So I have little more to talk about and what is the minimum required of the topology to have a meaningful thing. Suppose if usually I want it like if the sequence converges to x and it converges to y, I want x to be equal to y. Even bare minimum, that is also not coming. That will come only when you have this kind of a situation. If x and y are two distinct quantities, I should be able to find open sets to separate this x and y. If you have such a thing, then anything that converges to x will no longer converge to y. Make sense? So there are separation actions to introduce later on, which gives you a reasonable topological space on which convergence may be more of the kind we always imagine. Okay. So let us see what would this really lead to. Okay. So there's a little problem. I'm going to take a family of topological spaces and their product. Alpha belongs to delta, is a family of topological spaces. Actually, you can take delta to be only a set of all natural numbers. That itself will give you a nicer example. Okay, you don't need to take a general abstract set. But if you have finitely many product topology and box topology are the same, so I'm not going to get any strange conclusions away from that of the product topology for the box topology. Okay, so suppose this is a family of topological spaces and capital X equal to product X alpha, alpha belong to delta, be the product topology. Okay, be the product space. Product with product topology. Okay, that's what I mean by product spaces. Okay, I take a sequence xn in X. Okay, it converges to an X in X if and only if every projection pi alpha of xn converges to pi alpha x in x alpha for every alpha. We can prove that. Okay, because if xn converges to x, any open set, even basic open set that contains x, and after a certain stage, all these sequences should sneak into that. Okay, but that open set I have taken will have in some component a genuine open set in X alpha. So that particular component should sneak into that and after certain state, and vice versa. Okay.
All the projections should be convergent. That's what we are saying here.
And vice versa. If all the projections converge, I better be careful. I don't know if I can say vice versa. Because I probably cannot say the vice versa. Because for each alpha, you have an n naught, and that n naught may depend on those things. I should not say if and only if. If xn converges to x, then I'm thinking, okay, I better be careful. Oh, okay, yeah. Yes, I can say that. కొంచెం ఆలోచించుకోవాలి. If and only if. Yeah, I can say that. You understand my difficulty?
No.
For each alpha, there may be n naught, but however, open sets, I mean, you do it for basic open sets. Basic open sets have only these G alpha nuts only in n components, and rest of the components are all full spaces. So for
Okay.
on those components only, I get maybe n naught one, n naught two, etc., n naught n or something. And amongst them, you can take the maximum, and that will do for everything. Okay? If and only if. You know, otherwise,
But
go ahead.
how can we say that there is a maximum and not one and
See,
not two?
when I take a basic open set on the right hand side, okay, it is a basic open set on the right hand side. How does the basic open set look like? It looks like pi g alpha, alpha belong to delta, but only finitely many
Yeah.
alphas. So g alpha k equal to some, g alpha is whole
Right.
x alpha for all alpha not equal to alpha 1, alpha 2,
Yeah.
etc. alpha n. Okay.
Right.
So when I look at the projections, the pi alpha one is continuous, pi alpha n xn converges pi alpha 2 xn converges, maybe say xm. Okay. So, right, when you say pi alpha 1 xn, pi alpha 2 xn, pi alpha m xn converge to appropriate those things, you have indices n naught 1, n naught 2, etc., n naught n in n, so that for all n greater than equal to each n naught k, okay,
Yeah,
amongst them, if you take it the biggest one.
but m need not be finite, right? So g alpha equal to x alpha. Oh, for a
No, m will
finite set,
be,
m is finite. That's what we're. Yeah, that's right.
m is
That's
finite.
m is
For
finite.
that g, m is finite.
Yeah,
So,
yeah,
right, I
yeah.
given g have bigger m. Who cares?
Another
For
m.
that g,
Yeah,
m,
yeah,
okay.
yeah. Okay, okay. So you can talk about a max of the of those n knots,
Yeah,
which
that will do
makes
the
sense. Yeah.
job. Okay. So this is true. Now I want to ask: is this true in the box topology? It is not going to be true in box topology. More than that, it becomes very bad. Actually, you will show that such a sequence will converge only on a certain stage. All the terms are one and the same. Okay, because you can get infinitely many of them.
Right.
You
That
cannot get the
then you can
maximum.
talk about maximum then. Yeah.
So you want everything to coincide. So what happens is the convergence of this turns out to be that after a few components, this is actually, this has no order or anything. Delta has no order or anything. If delta is like maybe natural numbers, x1 cross
Yeah.
x2 cross etc. cross xn cross. Suppose I have infinite many, then what happens is this sequence will converge there only when another substance all the elements are one and the same.
Yeah.
Another substance, it becomes a constant sequence. That's not a nice thing to talk about. Okay, that's okay thing. Why not? But unless it is constant, is what requires for that to be a convergence. So that's the problem. Okay, that's it. Wrong, and there will be issues here and there. Okay, I will give you more about these things when some counterexamples are required for some things. We can talk about these things later. Huh? All right, what I will do is maybe I'll stop here because we have to change the topic now. Huh? I can give you some more examples. So you can see Munkar's also has some examples. If you have maybe subset C alpha in X alpha, okay, pi A alpha alpha in delta cross closure is pi A alpha closure alpha in delta. So a couple of such results will come. Then you can look at some exercise in markers. I have not talked about many more things on these things, but we do talk about very important thing about project spaces. See, look, unfortunately, we don't have many things. We have separability, second countability, Lindelofness are only three properties we discussed. We have discussed lots of more properties, separation actions, compactness. Okay, then we ask. Uh, whether the individual places have this property, does the product space have the property or not? Like yesterday, maybe the previous class, I showed you that even if the individual spaces are second countable, the product space need not be second countable, right? I proved that for one particular example. I did that. Okay. So I asked this thing. So I need to introduce some properties, especially compactness. Some of you already know that. And then separation actions. I will introduce these things in the next class. Okay. And maybe in the next class, I can start there. I have to talk about little set theory I told you. Especially I need Jones lemma and action of choice. So maybe I will talk about set theory in the next class. Okay. And then go to compactness. Hmm? And what else? I'm not going to be here on Monday. I'm going out of town. Uh, I'm actually going to Chirala. Who is this? Kiran Kumar Yadav. I'm going to Guntur and then Chirala.
Okay.
uh, so I'll come back on Monday evening only. So we'll meet on Wednesday. And when we meet, I think we'll do a little set theory, not too much as Isodhar said. Don't go overboard on that. So I will just do 1 day of set theory. And next go to compactness. Okay, that's all for now.
Okay. Thank you.
Thank you, sir.
I finished.